Hi, this is week 5 of AP Physics, and this week we'll be looking at forces. So for our learning objective, we'll use representation of the center of mass of an isolated two-object system to analyze the motion of a system qualitatively and semi-qualitatively. So let's start with forces. A force that results from the physical contact between two objects is called the contact force. So for example, if I have this little remote on top of my hand, there it is making contact with my hand. That would be an example with a contact force. And gravity is pulling down on the little remote, as well as my hands pulling up, pushing up on the remote. And since they're equal, there is no movement because they're both balanced out. So the net force is 0. An observable force between two objects which are not in contact is called a field force. Now, let's talk about contact force versus field force. In this example, a man pulling on a spring, that will be a contact force. Again, they are touching. Here, a young lady pulling a little wagon, that would also be a contact force. She's pulling force on it. A football player kicking a football would also be a contact force again, even though for an instant the ball and the foot of the player do make contact. On the other hand, gravity would be another force that would be considered a field force. For example, two objects with mass will go ahead and pull towards each other, gravitational force. Also charges involved. If you have a positive and a negative, they have a force of attraction between opposite charges. So that will attract one to the other. Lastly, magnetic force. If you have a metal and you have a magnet, they will also pull themselves towards each other. And for these three field forces, notice that they're not touching each other, yet they do exert a force on each other. So we have contact forces and field forces as well. Let's go ahead and take a look at Newton's first law. In Newton's first law states that an object moves with a velocity that is constant in magnitude and direction unless a non-zero force acts on it. So for example, if I'm pushing on an object and putting force on it, that object will move in that direction. Okay, and now what if we were to just remove that force? Then force of friction will bring it to a stop and it will stop moving. So this will be two separate forces. Me pushing will be one force versus force of friction. More commonly, this is referred to as Newton's first law, like an object in motion will stay in motion versus an object at rest will stay at rest unless another force acts on it. If you were in space, you get a ball and you throw it, so you put force on it, that ball is going to keep on moving and it's not going to stop unless something gets in its way. So if it's in motion, it's going to stay in motion. But if an object's at rest, it will stay at rest. For example, I get the same ball in outer space and do not apply any force to it, so just hold it, and I don't put any force on it, it will just stay in the same spot. Now, it says a more common form of it is what I just mentioned. An object at rest will remain at rest, and an object in motion will remain in motion. Here we have Isaac Newton, and I put a little, I love calculus because aside from developing Newton's laws of physics, he also developed calculus. Second of Newton's law we're going to look at, and we're going to actually, that's the one we're going to use today quite a bit. It states that the acceleration of an object is directly proportional to the net force acting on it and inversely to the proportional mass. Alright, so the formula, I rewrote it here, but let's take a look at the ones that's here. Here they isolated the acceleration. Alright, first of all, let's talk about net force. So you could have forces, multiple forces acting on an object. For example, you could be pushing an object, so you're applying force from one end. That would be one force that's being applied. There's also force of gravity acting on it, but there's also force from the floor pushing from the bottom. And so you add them all up, and that will be your net force. When you put all the force from the top due to gravity pushing down, from the floor pushing up, from me pushing that sideways, add them all up, that's your net force. Okay, now inverses. The more force you have, the more acceleration you have. So those are directly proportional. That's what's referring to here. But the more mass you have, the lower the acceleration. Those two are inversely proportional. The unit to measure force is the Newton, and it is the same as 1 kilogram times meter per second squared. So that's the value for a Newton. Now let's go ahead and take a look at our next example. It's example number 10. In this example, it says an airboat with mass of 3.5 times 10 to the 2, or 350 kilograms, including the passenger, has an engine that produces a net horizontal force of 7.7 times 10 to the 2 newtons. After accounting for the force of resistance. So they're giving us just the net force. So I'm going to go ahead and write down two things that are given to us. Mass, it is 350 kilograms, and the net force, after accounting for resistance from the water, it is 770 newtons. Part A, find the acceleration of this airboat. So that'll be a part A. So we're going to get this formula, rearrange it slightly. It's force equals mass times acceleration. And I want the acceleration of the boat, so I want to get rid of the mass. So acceleration is just the force over the mass. Force is 770 newtons. Mass is 350 kilograms. You simply divide, and that will give us the answer for A. Our airboat's accelerating at 2.2 meters per second squared. Now if you're wondering how do we get meters per second if you have newtons and kilograms, remember that a newton has kilograms times meters per second squared, and the kilograms get cancelled out here, so leaving behind just meters per second squared. That's where the unit came from. That takes care of part A of example number 10. Let's go ahead and move on to part B. In part B it says, starting from rest, how long does it take the airboat to reach a speed of 12 meters per second? Okay, for that one, I'm going to go ahead and use this formula. Oops, times 0 plus acceleration times time. I want to know how much time does it take. Now, it's starting from rest, so velocity here is 0, so I'm going to ignore that. So there's our formula. And I want the time, so I want to divide by acceleration on both sides. Alright, so there we have it. And so it's just time is really the velocity, and they wanted a velocity of 12 meters per second, and divided by the acceleration. So time is equal to 12 meters per second, divided by our acceleration, which you have it here of 2.2 meters per second squared. And everything's going to cancel out except for one of the seconds. That's going to be our unit. So it gives us 5.45 seconds. That's our answer for part B of example 18. Alright, up next is part C, and in this one they ask you, after reaching that speed, the pilot turns off the engine and drifts to a stop over a distance of 50 meters. Find the resistance force, assuming it is constant. The water's putting resistance, a force of resistance against our boat, so it's moving towards the right according to our diagram right here. Okay, so let's see, let me write down what we had originally. Now in part C, the driver turns off the engine. So now the only force being applied on it to slow down the boat is going to be the resistance from the water. Okay, so let's go ahead and take a look at that. We have a distance. It travels a distance of 50 meters. And the velocity that it's traveling at, it was 12 meters per second. Now, the velocity that's going to end at, they want it to come to a full stop, it's going to be 0 meters per second. Now, that's the first part of the problem. This is the second part, so we're going to label that as VO because you started at 12 meters per second, and now it's going to come to a full stop. So how much force did that take? Alright, so what we're going to go ahead and do is we're going to go ahead and solve for the acceleration of the boat. Then we're going to plug it in here to solve for that force. So that's going to be our strategy. Alright, we have the velocity, we have the distance, so we're going to go ahead and use this formula. to solve for the acceleration. Alright, so I'm going to go ahead and move this over here. I want to isolate the A. Now I'm going to divide by 2 and divide by the distance, the displacement, I'm sorry. So we're going to move it over here. Now it's going to give us our acceleration. Now once we have it, again, we're going to plug it in here. We do have the mass, and that's going to give us how much force being applied. Okay, now at the end we have a zero velocity. So I could just cancel this out, giving me this formula, just simplifying it a little bit. Alright, so let's go ahead and plug in the values. So it's going to be 12 meters per second squared. The negative's outside of the squared. 2 multiplied times the distance of 50 meters. And that's going to give us our acceleration, which is a negative value. And the reason why it's negative is because this boat is slowing down, so therefore acceleration is working against them to slow them down. So it's going to be 144 divided by 100 to be 1.44 meters per second squared. That is the acceleration of the boat because it is slowing down. It's negative. Okay, now they want to throw the force. So how much resistance force is being used? That's going to be acceleration times the mass. So we multiply both of those. Force equals mass times acceleration. So the force equals the mass of 350 kilograms. Multiply times our acceleration of negative 1.44 meters per second squared. Multiply both of these and that will give us our answer. Alright, and it is negative 504 newtons. Negative because it's going against the movement of the boat. If our moving is going in this direction, the force acting on the opposite, which is slowing it down to a full stop. Okay, this brings us to the end of problem number, or example number 10. Up next for us is problem number 19. This problem piggybacks on the previous problem that we had done, and so it's the same airboat. Now they ask us, suppose a pilot, starting again from rest, opens up the throttle part way. At a constant acceleration, the airboat then covers a distance of 60 meters in 10 seconds. Find the net force acting on the boat. Alright, so to find the net force acting on the boat, we're going to get the acceleration first, then plug it into this formula, and we're going to get our answer. So, the formula we're going to need is this one. Displacement equals velocity initial times time plus 1/2 acceleration times time squared. We have the time, initial velocity, we have the displacement, that's going to give us the acceleration. Alright, so let's isolate the acceleration. First of all, we're going to start with this. VO is 0, so 0 times time is just 0. So that's gone. So it is 1/2 acceleration times time squared. I'm going to isolate the accelerations. I'm going to multiply it by 2 and then divide it by time squared. So it's going to give me 2x multiplied by 2 so I can get rid of the half. And then I divide it by time squared. So there you have it. That's our acceleration. Now I want the force. I'm going to get that acceleration, plug it in here. So it is force equals mass times acceleration. I'm going to get this, which equals acceleration, plug it in here. So our answer is really force equals mass times 2 times displacement over time squared. Alright, see there's an A. I substituted A, that value there. Okay, I'm going to extend that line. Looks a little bit better that way. So let's go ahead and plug in all these values and solve for the mass. Mass of the boat was 350 kilograms. Multiplied times 2, a distance of 60 meters. Divided by the time squared. So get your calculator. That'll be 350 times 2 times 60 divided by 10 times 10, which is 100. So that gives us 420 newtons of force. Positive because it's pushing the boat forward. So that'll be the answer for this problem. Alright, let's go ahead and move on to our last problem, which has parts A, B, C, D, E, and F. Alright, in this problem they ask you which of the following statements are true. Statement A, an object can move even when no force acts on it. Okay, let's say that again you're in space and we throw the object and now it's in motion. So you've let go of it, there's no force acting on it now. Previously I put force on it, but once I let it go, there's no more force acting on it. So is that object in motion? Yes. Are there any forces acting on it? No. So therefore that statement is true. Yes, an object can be moving even though there's no forces currently being applied on it. Though, gotta say, initially there had to be a force to get it to get going. Alright, if an object isn't moving, no external forces are acting on it. Not true. That one is false. This pen is not moving, but there's a force of gravity pulling down on it. Equally, there's a force from my hand pulling up on it. Okay, but it's not moving at all, but there are forces acting on it. Letter C, a single force, if a single force acts on an object, the object then begins to accelerate. Yeah, force will give you acceleration, that is correct. And if there's only one single force and there's nothing countering it, then yeah, there's definitely going to be acceleration. So if there's a singular force, yeah, there'll definitely be acceleration. Alright, part D says if an object accelerates, a force is acting on it. Yeah, acceleration is equal to the mass times the force, so therefore if there is acceleration, there has to be a force. So that statement is true. Letter E, if an object is not accelerating, no external force is acting on it. Again, same thing. Is this accelerating? No, it's in the same spot, but there is gravitational force acting on it, so that one will be a false statement. Last one. If the net force acting on an object is in the positive direction, and the object moves only in the positive direction, that is not exactly true. Alright, so for example, you have an object going very fast, and you begin to slow it down. So it's moving in the positive direction, it's moving positive that way, but you can have a force in the negative direction, and that will begin to slow it down and slow it down and slow it down, eventually get it to stop. But you can see how you could have an object moving in the positive direction and a force going in the negative direction. So it is possible. So therefore that statement will be false. Okay, this brings us to the end of Unit 1 in AP Physics, which is kinematics. Thank you so much for watching.